Hi everyone, I'm Quan. I'm from University of Washington. And today I will represent the author here to present their work, Efficient Performance-Aware GPU Sharing with Compatibility and Isolation through Kernel-Space Interception. As we all know that the GPUs have become more and more powerful nowadays. For example, back to 2017, we have V100, which only have hundreds of T-flops. But now H100 or B100s, they have thousands of T-flops. And the similar trend is also observed from the AMD side. For example, their MI100 only have 100 T-flops, but in recent years, MI300, MI325, they also have a much higher T-flops. However, there are still some lightweight tasks that do not require that beefy GPU to run. For example, these lightweight tasks only maybe require a fraction of GPU to achieve their performance targets. In this case, if you still allocate the whole GPU for that application, it is overkill. So you are basically wasting your GPU resources. So what we do is using GPU sharing, which means we want to run multiple tasks in one GPU simultaneously. If you look at the system stack of the GPU sharing, you will see that here I'm first demonstrating 3 applications. Some of them are running inside a container, some of them are just bare metal. Different tasks can rely on different frameworks like Unity, TensorFlow, or PyTorch. And they will also use different runtime like Wacom, CUDA, CUDA 11, and CUDA 12, basically. So all these applications will send API calls to the user mode GPU driver, which we call as UMD. This UMD will further send in system calls to the kernel mode driver, and that will further use the memory maps I/O to control the actual GPU hardware. So what a GPU sharing is basically you want to intercept these messages across different layers. What you can do is you can first of all intercept at the API call level, or intercept at this system call level, or the MMIO level. So in this case, we want to intercept this request and try to either delay it or schedule it based on the sharing portions. In terms of GPU sharing, there are different targets. The first one is a capability, which means allowing tasks with different runtimes to be co-located. Also, you want fault isolation, which means failure on one task will not affect other tasks. Finally, is for the performance isolation, which means that for every task, you want it to reach the performance target. However, existing solutions fall short on the capability and the isolation. So first, here I'm showing different ecosystems, different runtimes, and different libraries. Some API remoting-based systems also only works with a particular CUDA version. And MPS and MIG, they are provided by the vendor, only have limited scopes. However, what we are aiming at is full coverage over CUDA, over Wacom, and OpenGL, any application that's run on the GPU. Moreover, as for the fault isolation part, existing systems are under the attack of those adversary applications. So for example, here, if you use API remoting, then adversary application can cause out of memory for all the victims. And as for the MPS-based solution, adversary can also use cross-border accesses to make other processes terminated. So our key insight here is to ensure the capability and isolation. We need to intercept the request at the kernel space. Specifically, the unimode driver will write commands to the command buffer and will issue system calls to the kernel mode driver. In this case, what we want to do is to intercept those 2 requests. So we are doing at this level because if we do it one level higher, say if we capture all the API calls, then we need to manually dealing with different runtimes, which is a burden. If we do it in a more lower level, say we control the memory maps I/O, then that part we need to maintain different GPU context for different GPU tasks, which also increase implementation difficulties. So apart from this weak capability and the fault isolation, in the performance side, existing systems also fall short. Here I'm showing different scenarios that we collocate in different tasks. As you can see here, existing solutions incur very large variations between different tasks, and some of the time it's below the performance target, which is obviously not desired, and some of the time it is above the target, which we claim is also not good because you are allocated too much GPUs to that application, so there is a waste. The reason behind this fluctuation and this efficiency comes from they either use spatial partitioning or use temporal partitioning. So first of all, I'm showing you a 50% time sharing. In this case, because your GPUs are very beefy and your workload is very light, so you cannot use all the SMs. So for example, here you may only use 44% of SMs, meaning that the rest of GPU is basically wasted. In terms of spatial sharing, you don't have the flexibility to cut the GPU into arbitrary instances. So for example, if you assign a slightly larger instance to a particular workload, then you are wasting the GPU in a time scale. So our insight is that we need to use spatial-temporal orchestration to have the higher utilization of the GPUs. All right. So in order to provide that support, we propose this KRYPTON, which is a kernel-space GPU sharing mechanism that aims to guarantee the performance of the applications as well as capability and fault isolation. So this includes multiple modules. For example, here a profiler will do some offline profiling of the applications to know what time sharing is needed for this application to run on a particular instance of the GPU. And then we have this spatial-temporal orchestrator, which will make the decision which instance we run and what is the time sharing for this application. Also, the KRYPTON includes one scheduler for each of the GPUs that take care of the time sharing and take care of the interception. So now I will dive deep into these modules. So first part is about the spatial-temporal orchestrator. So it will identify the minimum MIG that can run the workload to satisfy the performance target. So in this case, in the second step, different tasks that will assign to the same instance will be packed together. In the third step, we will try to migrate those applications running on small instances to the larger instance to try to pack the resource together. So note that the time sharing for the application is also reduced because now you are running with more GPU resources. Finally, these multiple instances are packed to the physical GPUs. So at this step, we already determined which application will run which GPU and run which MIG. So after that, what we need to do is to control the accurate time sharing that we derived in this step to make sure every application reaches target performance. So in order to do that, we have this feedback controller. In the default mode, which is passed through, then basically different processes just launch kernels arbitrarily, and they will be scheduled on the GPU. You don't have any control of the GPU time sharings. A better way, maybe you use the sleep to kind of limit the rate of submitting new kernels. In this case, you have some control over the GPU utilization, but the kernels and CPUs, they run asynchronously, which means you still do not have the full control over how many time slices of the GPU are owned by each of the process. So in this work, what we do is we first assign a CPU token for each application so that, for example, if the process holds this token, it can issue kernels to the GPU. For the lasting kernels, we will keep monitoring the GPU usage for different processes. So if we find out that one process is actually doing more work than it should be, then there will be adaptive token control to compensate the victim process. For example, here the process 1 have some long-running kernels that occupy the GPU time sharings for the process 2. Then in compensate, we will just give process 2 more tokens so that we ensure a fair GPU sharing. So finally, we want to make this time sharing happen, and we want to control the kernel launches. In order to do that, the KRYPTON uses the interception module. So in this case, this module will try to lock the command buffer. So the locking here means we make it read-only. If a process wants to write some commands to issue a new kernel to the GPU, it will trigger a segmentation fault because now it's read-only. And this fault will be handled by a signal handler here. The signal handler will ask the kernel-space interception module to see if this process is holding a valid CPU token. If it's actually holding a token, then we will unlock the buffer and let this write command go. Otherwise, we will delay this write command to make sure the other process can own this GPU for this time sharing. All right, finally, I will talk about some evaluation results. The KRYPTON is evaluated on this A100 platform and 4090 platform. So we use various workloads, including deep learning workload, training, and inference, also some graphics workload, like renderings. We set different performance goals here, as you can see in the throughput requirement, which is a fraction of the optimal throughput. So here is the evaluation result. On the first row, I'm showing the performance of the system compared to temporal only, preference to GPU-led MIC, and other existing systems. So we are able to reduce the number of GPUs by 32% because our orchestration process. In particular, if we look at this case, we are able to pack 20 different applications onto 4 GPUs, use both temporal and spatial methods. In terms of the throughput, as you can see here, again, this 1 here means a normalized performance, normalized to the target performance. So if any bar is below 1, then it's not satisfied at performance target. If it's over 1, then there's an overkill. As we can see that the KRYPTON tightly follows this performance target and slightly above this performance target 1. In terms of the Vulkan applications, because we intercept those requests at the kernel level, so we can support all different combinations of the workload. Again, the red bar showing the expected performance, and the blue bar showing what we actually achieved. So in all the cases, like 2 Vulkan applications, 3 Vulkan applications, and Vulkan and CUDA applications, we all achieve a very tight match of the performance. So in this part, we dive deeper into the ResNet 50 training applications, and we set different performance goals from 2575 to more fine-grained simulations. In all of the cases, KRYPTON can maintain a very accurate performance for any of the instances, while existing system falls short on some part of the performance goals. If you look at the GPU utilizations of different GPUs, you can see that the KRYPTON is able to maintain a very stabilized utilization at 25 and 75%, while other systems have very large fluctuations. Okay, so in conclusion, we present KRYPTON, which uses a spatio-temporal orchestration policy that efficiently reduces the GPU fragmentations. We also use a feedback-based performance control policy to ensure proper time sharing. And finally, we include a kernel-space interception that ensures the compatibility and isolation to use the GPUs. All right, thanks everyone. And if you have questions, feel free to reach out to the first orders as I listed here. Thank you.